Hello AP Chemistry and welcome to the closing demos for Chapter 20, right? Where we are going to take what we've learned, right, and put it all together, right? Where you are going to show that you understand what redox means versus what an electrochemical cell means, and how we can take those two, right, and make them do what we need them to do. All right, so first of all, when we say what is a redox reaction, what does that mean? Right. It means that we have reduction and oxidation, right? Something is being reduced, right? Meaning it is gaining electrons, right? And something is being oxidized, right? Or losing electrons, right? And they have to happen together, right? We've been talking about that since chapter 4, right? We can't have them in isolation because the oxidation is what produces the electrons that the reduction reaction subsequently uses, okay? Now, all year, we've been talking about it happening in one pot, right? Wherein we put a piece of metal in an aqueous metal chloride solution or something like that, right? And then the reaction happens in there, right, on the surface of the metal, okay? But we can take that concept, right, and now turn it into an electrochemical cell, where what's the difference in an electrochemical cell? Right, so we still have the concept of redox, right? We have something being oxidized and something being reduced, right? But they are separated, yes? So that we can harness the electrons, right? So depending on the type of cell it is, we are either harnessing the electrons to do work, right? So those would be the types of cells where we have a cell, and we have here a light bulb, for example, right? Let me label that in case you can't tell what that is, right? A light bulb, where we would be harnessing a cell to do work, right? Or, right, on the flip side, we could be doing like we did in the other demo, right? Where we have a battery or a power source that does a certain amount of work, right? We could also just label this with whatever voltage it happens to be, right, to get the job done. Okay, so then that's what differentiates the two, right? Redox is just the concept of having oxidation reduction. An electrochemical cell means they are separated so that we can either harness those electrons, right, or use electrons to make that happen in a very specific way, okay? So it says that we're going to observe reaction 1, right? So now, since we're given a reaction, we already know this reaction says that copper undergoes what? Right, copper is oxidized. And alternatively, what happens to this? Right, this goes from Fe3 plus to this, right, means this is reduced, right? So that's the reaction that we are proposing, right? Is it a redox reaction? Clearly, right? Is it an electrochemical cell? Right, you can't answer that without seeing the setup for the process, yes? So here, all right, so we've got our iron 3, whatever I said, and we've got our piece of copper, which I have put into the solution, and they are hanging out, and what do we observe? Correct. Your observation is correct. Nothing. We observe nothing. All right, let's talk about that. So, should we observe nothing, right? So for the reduction or the oxidation of copper, right, that would be negative 0.34 volts, right? And for the reduction of iron 3 plus to iron solid, that is negative 0.04 volts, right? Which means that should this exhibit a reaction? No, right? We have a negative voltage, right? So if we use our delta G equals negative NFE, right? Obviously, this is not a thermodynamically favorable process, right? Which means that no, we are not going to observe anything, right? Is it an electrochemical cell as set up? No, right? Because my reactions are not separated. Everything's happening in this one bucket together, so there's no way to take advantage of electrons, right? Or tease those electrons out so that way we can force certain types of reactions and results. So, could it be made into one? Absolutely, right? Specifically this kind, right? Because it's got a negative cell voltage, right? In that we could have one electrode that has a piece of copper, right? And we could have one electrode, let's say, inert, right? And so we could get oxidation to occur here, right? Meaning this would be our anode, right? And we could get reduction to occur here, which means that we're going to get our Fe3 plus to reduce down to Fe solid, right? So we basically iron plate whatever that electrode is, right? We would need a power source, right? And then we would need a solution for them all to swim in. So this would be our iron chloride solution. Yes, does that make sense? Now we will have taken advantage of it so that way we can then get iron plating over here, right? And we will get the oxidation of copper on the other side. Yes? Now we've turned it into an electrochemical cell. All right, next up, observe reaction 2, steel wool and a 9-volt battery. All right, so there we have some steel wool, where what is steel wool? Right, steel wool is just thin threads of iron, and then we've got a 9-volt battery that we are touching to that steel wool, or very thin threads of iron, and we are seeing, oh, look at that, all those, it's turning red, which is an indicator of, right, that's just, you know, a little bit of, you know, you should be able to tell me. See, here's the problem. Now I'm just talking to myself. But anyway, definitely a sign of heat being released, yes. So much heat, in fact, right, that we are basically, that's a tiny fires, right? That's what that is, right? All that sparking is there's so much heat being released, right, that we are getting some fire from our reaction, right? Clearly, if we look here, it should be clear that a reaction has occurred, right? Because we've got a little bit of gray up here from the parts that haven't reacted, and the rest of it is kind of like a bluish color, and that would be where the reaction occurred, right? And we'll see that there are crumbles sitting on the bottom of the plate, which means that the process has changed, right? Whatever the steel wool was into something that is new and different. Yes, does that make sense? So, that being the case, now that we've seen that, which, by the way, if you ever watch like those survivalist shows, they're like, ooh, need to start a fire, get some steel wool and a 9-volt battery, as if those are things that are just laying around everywhere, right? But, you know, just as an FYI, right, that's what one could do. So anyway, steel wool, 9-volt battery, right? So when we touch the battery to the steel wool, right, so first of all, is it a redox reaction, right? I think clearly the answer to that is yes, right? So we have our steel wool. Okay, I don't even know why I'm drawing this. I don't know how to draw this. This is ridiculous. And our electrodes, right? And we would touch our battery to it, and we get the reaction to occur. So if we look at our options, we have solid iron, right? And it's probably being oxidized, right, to either iron 2 plus or iron 3, whichever, right? But obviously the oxidation is going to be positive, right, and thermodynamically favorable, whichever one occurs, right? We would have to do some type of analysis on that bluish product that we produced to see if that's iron 2 plus or iron 3, okay? And then so we got to look at what is the plausible reduction reaction. Just this one, right? So clearly we're getting the oxidation of iron. And again, whether it's to 2 plus or 3 plus, we would have to do some type of chemical analysis on the bluish stuff produced to know which product it is, right? But clearly the reduction is O2 because that's the only thing that's available, right? Now if we look, this is, right, plus 1.23, right? These are definitely plus. So this has definitely got a positive E0 value, which means if we do delta G equals negative NFE, right, thermodynamically favorable, right? And so redox, yes, right, clearly. Is the electrochemical cell? No, not as it is set up. But could it be made into one? Absolutely, right? We could have a half cell that is, or we could have our steel wool, right, which would be our iron, right, which would have to be connected to an electrode, which would then have to be connected to a voltmeter, right? Or a battery or a fan or something, right? And we would have to have another electrode, right, that is exposed to oxygen, right, just open to the air. And we would have to have a salt bridge that connects these two. And you can go look at some of those options online, right? But this reaction is important for a lot of things, right? So as an electrochemical cell, right, we use the concept of metal oxygen batteries, right? So, and they're separated, usually they're solid state batteries, but we use metal oxygen batteries to power certain devices, right? Because they can be relatively lightweight, And, right, they get the job done very efficiently, right, and they are thermodynamically favorable, right, and we can harness those electrons. In addition, right, this reaction is also used if you ever have those little hot pads, like those hand and foot warmers that you would carry around in the winter. That's the same exact thing, right? That is the oxidation of iron, right, and reduction of oxygen gas, right, then produces heat, right? It's just, it happens in a specific way, so that way it doesn't produce too much heat, right, such that it sparks, because that would be problematic. But that's why, right, it's like, oh, if you need to refresh it, take it out of your pocket, give it a good shake, right, and then put it back in there, right, give it a little bit more oxygen, basically, right, so that it can do its reaction, right, at a controlled rate. So it's not just iron, right, there's also, I believe it's carbon in there to help control the rate of the reaction, right? So anyway, life things we should know. All right. I hope you are doing well, and I hope I will get to see you soon. And yeah, all right, be good. Have a lovely